Hello everyone, in this video we shall continue covering topic 5.4, dissolving ionic substances. This section will cover or consider the enthalpy changes that occur when ionic substances dissolve in water. I will start by first going over a definition that we learned in subtopic 5.1, which is the standard enthalpy change of solution, of solutes, delta H solution, which is stated here. The definition states that it is the enthalpy change when 1 mole of a solute is dissolved in excess solvent to form a solution of infinite dilution under standard conditions. I have stated an example here for NaCl, an ionic compound, which is NaCl solid. When it is dissolved in excess H2O, which acts as the solvent, the ions separate into aqueous ions, which are solvated by the water molecules, Na positive aqueous and Cl negative aqueous. This process is either endothermic or exothermic, depending on the solute being solvated by the water molecules. This definition states infinite dilution over here. What infinite dilution means is that any addition of extra water does not affect the enthalpy change or does not produce an enthalpy change, meaning that the ions are completely separated and do not interact with one another. They are only solvated by water molecules, meaning they are infinitely dilute. I have stated this here. Infinite dilution means that any further dilution, which means addition of water solvent, of the solution produces no further enthalpy change. What this means is that the solute is completely dissolved and there's no interactions between the ions. Meaning, which is stated here, meaning the solute particles exhibit no interaction with each other in solution because they are at infinite separation from one another. Meaning they're solvated by the water molecules. We have studied this in topic, as I've stated, we've covered this in subtopic 5.1, and this process could be endo or exothermic depending on the solute. I would like to point out that like all other definitions, this states here it's the enthalpy change when 1 mole of a solute is dissolved in excess solvent under standard conditions. As you can see here, this is 1 mole of NaCl, which would produce 1 mole of Na plus aqueous ions and 1 mole of chloride -1 ions. If this were MgCl2, for example, which I will cover in a bit, it would produce 1 Mg2 plus ions plus 2 Cl minus ions, 2 moles of Cl minus, but this would still be for 1 mole of solute. I will discuss this in a bit. I have also placed the data booklet values for the standard enthalpy change of solution values, and as you can see here, they have listed many enthalpy changes for many solutes, enthalpy changes of solution, some of which are endothermic and some of which are exothermic. This is table 19 in the data booklet. This is table 19, which covers the enthalpy changes of solutions, of solutes. This definition has already been covered. A new definition that we will learn is the definition for the standard enthalpy change of hydration of ions. This definition states it's the enthalpy change when 1 mole of gaseous ions, is surrounded by water molecules to form an infinitely dilute solution under standard conditions. Infinitely dilute, which means the exact same thing as we discussed previously. It's basically bringing a gaseous ion which has no interaction with any other particles. Thus, it is highly unstable because its charge is not being stabilized by any other interaction, and dissolving this gaseous ions in water. That's what is meant by surrounded by water molecules. It's basically bringing a gaseous ion and bubbling it through water. It would form ion dipole interactions with the water molecules. It will form interactions between the ion and the dipoles in the water molecules, which surround the ion and solvate it to produce a much stable ion in solution, and thus this definition is always exothermic. standard enthalpy change of hydration of all ions, whether they're cations or anions, are exothermic because they are initially highly unstable as gaseous ions, but once they are dissolved in water and they form interactions, ion-dipole interactions in water. Basically, they are solvated by the water molecules, thus stabilizing their charge. They would form much more stable ions and thus would release energy, making this process exothermic or always exothermic. The definition, I've stated examples for the definitions here. As the definition states, it's when 1 mole of gaseous ions is solvated in water and thus forming an aqueous ion, which is solvated by water, whether it's a cation, as I displayed here using a sodium cation, or whether it's a chloride anion. It's the exact same process. It's a gaseous ion over here, and once it's solvated by water molecules, it becomes an aqueous ion, which is more stable. This represents the enthalpy of hydration of gaseous ions, which is, once again, as I stated, is always exothermic. I have stated this already, but I will read this for you and elaborate some more. It's basically, once the gaseous ions are dissolved in water, ion dipole forces of attraction form between the ions and the water molecules, which stabilize the ions once in solution, and thus the hydration enthalpies are always exothermic. As you can see here, the water molecules have dipoles, meaning they have a side that is partially positive and a side that is partially negative, and thus they can solvate both negative and positive ions. I've shown this here. The oxygen atoms would surround the partially negative oxygen atoms would surround the cation, engulfing it in a cage, forming ion dipole interactions, which I've clarified over here. As you can see here, the positive cation. The oxygen would surround the positive cation and form ion dipole interactions or forces, electrostatic forces of attraction, thus stabilizing the cations. This is a 2D cross-sectional diagram here, and thus 2 water molecules are missing, one above the plane of the screen and one behind the plane of the screen, as shown in this diagram here. On the other hand, if it were a negative ion, the partially positive hydrogen atoms in the water molecule can solvate the negative ion and form ion dipole forces of attractions, which would stabilize the ion in solution. As shown here, the chloride ion is surrounded by the or forms ion dipole interactions with the hydrogen, partially positive hydrogen atoms of the water molecule. I have also displayed the values for the enthalpy change of hydration values are listed in the data booklet in table 20, as you can see here, and they are all exothermic values. They have listed the enthalpy of hydration for some cations and for some anions, as well as polyatomic ions over here, and all values are exothermic because the enthalpy change of hydration is always exothermic. We can use definitions that we learned, such as the enthalpy change of solution, as well as the enthalpy change of hydration of gaseous ions, as well as lattice enthalpies that we covered in subtopic 5.4, to construct cycle to calculate the enthalpy changes of solution of many different solutes, ionic solutes to be more specific. As stated here, one can construct an energy cycle to determine the enthalpy change of solution of an ionic compound using these experimentally determined values, such as the lattice enthalpy of the ionic compound, as well as the hydration enthalpies of the ions in the ionic compound. This is what we will be covering next. I will use sodium chloride as an example. And thus dissolving sodium chloride in water, as stated here, can be broken down into 2 separate processes. The first is the lattice enthalpy, which is an endothermic process, and it involves the breaking apart of the lattice into gaseous ions, and thus basically it's the breaking of the ionic solid into gaseous ions. The second stage of this cycle would be the hydration of these ions, which is surrounding the gaseous ions by water molecules, which is always an exothermic process, as displayed here. I've displayed the cycle for the sodium chloride example over here. As you can see, it has three main definitions. This arrow represents the enthalpy change of solution, which is defined as the enthalpy change when 1 mole of an ionic solute is dissolved in water to form aqueous ions in solution at infinitely dilute solution. What we would place here is the gaseous ions to construct such a cycle. Once we place the gaseous ions here and link the ionic solid to the gaseous ions, this represents the definition of the lattice enthalpy of ionic substances, which is the enthalpy change when 1 mole of an ionic solid is broken into its gaseous ions, and this process in this direction is always endothermic. The next stage would involve these gaseous ions dissolving in water or being solvated by water molecules, which would represent the enthalpy change of hydration of these ions. Thus, this arrow is actually represents two arrows, which is the hydration, the enthalpy change of hydration of the cation as well as the anion, keeping in mind the molar ratios over here. Thus, I have 1 mole of gaseous ions of each of the sodium and chloride ions. If this were magnesium chloride, I would have 2 chloride ions, and thus I would multiply the enthalpy change of hydration of chloride by 2, since the definition is per mole of a substance. I will use the same example in a bit. Thus, if we were to calculate the enthalpy change of solution using this cycle, we would move in this direction, and thus we would add all these enthalpy changes. We would add the lattice enthalpy of sodium chloride, as well as the enthalpy change of hydration of the cation and the anion multiplied by their molar ratios as stated over here. Thus, the enthalpy change of solution equals the lattice enthalpy of sodium chloride plus the enthalpy change of hydration of the sodium ion plus the enthalpy change of hydration of the chloride ion. Overall, the enthalpy change of solution would be exothermic if the enthalpy changes of hydration were more negative than the lattice enthalpy is positive, and vice versa. I've stated this here, and I've added another cycle to represent it. It states here, overall, the enthalpy change of solution. Overall, the enthalpy change of solution will be exothermic if the total enthalpy of hydration of both the cation and anion is more exothermic than the lattice enthalpy is positive. This would form exothermic enthalpy change of solution. But if the lattice enthalpy were more positive than the enthalpy of hydration is negative, then the enthalpy change of solution would be endothermic. Therefore, the enthalpy change of solution could be either exo or endo. The lattice enthalpy in this direction is always endothermic, as we learned in previous videos, and the enthalpy change of hydrations are always exothermic when going from gaseous ions to aqueous ions. In general, if I were to write a rule for this, a mathematical equation, therefore the enthalpy change of solution would always equal the lattice enthalpy of the ionic compound plus the enthalpy change of hydration of the cation multiplied by the molar ratio, of course, plus the enthalpy change of hydration of the anion multiplied by its molar ratio. To be more clear, I have used the example of MgCl2 over here. And I have constructed a cycle as well to calculate the enthalpy change of solution of magnesium chloride. As you can see here, to construct the cycle, we would first place 1 mole of the ionic solid over here, ionic compound, and I would draw the definition of the enthalpy change of solution, which is the enthalpy change when 1 mole of an ionic solid is solvated by water molecules under standard conditions to form aqueous ions, as you can see here. And you should note that the molar ratio of magnesium is 1 mole because I have 1 mole of magnesium ions in the formula, and the molar ratio for the chloride ion is 2 because I have 2 moles of chloride ions in the ionic compound. And then I would link the cycle as I discussed previously. This arrow in this direction represents the endothermic lattice enthalpy, which is the lattice enthalpy of dissociation. And these two arrows would represent the enthalpy change of hydration of these gaseous ions when being surrounded by water molecules, and this definition is per mole. Thus, I have 1 mole of gaseous of magnesium cations being solvated or surrounded by water molecules. Thus, I would multiply its hydration by 1. But in this case, I have 2 moles of gaseous chloride ions being hydrated or surrounded by water molecules, and thus I would multiply this value by 2, the enthalpy change of hydration of the chloride ion by 2. Therefore, the enthalpy change of solution of magnesium chloride would equal the lattice enthalpy of magnesium chloride plus the enthalpy change of hydration of magnesium ions multiplied by 1 plus the enthalpy change of hydration of chloride ions multiplied by 2. You could get a question in which you will be given or you can use the data booklet, of course, to get these values, the lattice enthalpy as well as the hydration enthalpy changes for both ions, and thus you can calculate the enthalpy change of solutions. In other examples, you might be given, or you can use the data booklet as well to use the value of the enthalpy change of solution, and any one of these values could be missing, and you could be asked to calculate it, and thus you can simply place it as x in the cycle or in this mathematical equation over here and solve for x. This is basically the new cycle that you can use to calculate the enthalpy change of solutions of ionic solids when dissolving them in water. And a quick recap, as we discussed previously, it involves 2 steps, or we can think of its dissolving in water in 2 steps. We can think the first stage involves breaking the lattice ionic structure into gaseous ions, and this represents the lattice enthalpy, and then dissolving these gaseous ions or hydrating them by surrounding them by water molecules to form aqueous ions. And thus a cycle can be constructed as shown here, and the enthalpy change of solution can be calculated by simply adding all these enthalpy changes, since we will move along the arrows in this cycle. We will move along all arrows. We will be moving along this arrow and along this arrow and this arrow in the same direction, and thus no signs need to be flipped, and thus it's a rather simple cycle. You can either use the cycle, or you can either use the general mathematical equation for this cycle, as I stated over here. Which the enthalpy change of solution equals the lattice enthalpy of the ionic compound plus the enthalpy change of hydration of the cation plus the enthalpy change of hydration of the anions multiplied by the molar ratios. Please watch the next video, which will cover factors affecting the enthalpy change of hydration, how exothermic the enthalpy change of hydration of an ion is, and these factors are the same factors that we studied or that would affect the lattice enthalpies of ionic compounds, which are the charge of the ions as well as their ionic radius. Please watch video number 2. Thank you for watching.